This time, we will look at the 8-bit timer counter. Registers as the second part of the timer counter. This is the second content in the timer counter. I continue to explain things and then go through various exercises at the end. There is an 8-bit timer counter register, which is the most important register among timer counters. TCCR 0. Timer counter 0. Control register. Contains the mode and comparison output match for the timer. Next, we define the prescaler. The bit structure is as follows. For a total of 8 bits, the prescaler is determined from bits 0 to 2. And the mode is determined from bits 3 and 6. Based on this mode, the output comparison match will be determined by pins 4 and 5. The decision will be made in bits 4 and 5. So first of all, let's look at the function in the top 7-bit. A forced output comparison function will be performed. This bit is only valid non-PWM mode. If it's 1, the values set above for COM01 and COM00 bits are immediately output through the comparison output terminal. OC0 pin. It will be a bit that has the function of being output immediately. Does not generate interrupt. When you read it, the value of 0 is always read. And then in CTC mode, which uses the OCR0 register as the top value, it will be a bit that is not cleared in the timer. So, you won't often use FOC0. The exact bits you need to use will be waveform generation mode 00 and waveform generation 01 here. This will be the bit that determines the operation mode of the timer counter. As you can see, the operation modes are divided into normal, phase correct PWM, CTC, and fast PWM, and the corresponding WGM bits can be set in 4 cases. The OCR0 update timing is as you can see. And please be aware that the timing of setting the flag for timer overflow 0 is also determined by the timing shown here. If you look at Code Wizard AVR, you can see normal, phase correct PWM, CTC, and fast PWM in the modes. By selecting this, you will automatically be able to easily set up the wave generation mode. I will be able to set it up. For reference, what should I be careful about? In CTC mode, the top value is set to OCR0. Please be aware that in CTC mode, the top value is set to OCR0. So if you check the overflow interrupt and compare match interrupt here, C language code is automatically generated like this. When we get to this point, we first looked at WGM01 and WGM00. Now look at the comparison match output modes, COM01 and COM00. This pin plays the role of controlling the shape of the output. Waveform output through the OC0 pin. This determines the compare match output of timer counter 0. So, the output of this operation mode is determined according to the following modes. So, bit 4 of DDRB must be set as output, and the OC0 pin must be set as output. So please know that it must be set to 1. Then now, we will look at the output function. When in normal and CTC mode, look at the output function. COM0, 1, and COM00 each have 4 cases. In normal and CTC modes, output operation is determined by the following. OC0 pin. So when it is 00, it is used as a normal I/O port and OC0 is not connected. Toggle compare match. Clear on compare match. And set on compare match. R. The corresponding output comparison matches here. This time, looking at the functions of COM01 and COM00 that are output to OC0 in the mode set to phase correct PWM. If it is 00, it only operates as a general I/O port, and OC0 becomes disconnected, and the output is blocked. In the case of 10 and 11, respectively. If it's 10, it is cleared when it encounters OC0 during upcounting. So, if you keep following along, you can see upcounting here. If you look at the purple arrow, you can see what the waveform was like. It's cleared. It means it went from high to low. Then, when a comparison match occurs, with the OC0 pin and downcounting, a set occurs. Setting occurs means that if you go to the green color and keep going down to where the OC0 output was made, during downcounting, it changed from low to high. The ability to create such a PWM waveform is the function of phase correct PWM. So the two are the same as you see. If you set the inverted PWM method 11 to COM01 and COM00, the opposite inverse output occurs. So set and clear happen in reverse. So up to this point, we have looked at the output of phase correct PWM mode. This time, we will look at fast PWM mode. Fast PWM mode determines the output depending on how COM01 and COM00 are set. When you set it to WGM mode by the yellow bits, wave generator mode. As you can see, when it is 00, OC0 is also blocked as a normal I/O port. It means there is no connection. As you can see, in the case of 10 and 11, clearing occurs when it matches OC0 in the comparison match. At bottom, OC0 is set, so it becomes non-inverting. The opposite of this action is inverting. And conversely, when it meets OC0 in a comparison match, a set occurs. Clearing OC0 at the bottom is called inverting. So, you can understand that non-inverting and inverting mean that the waveforms are toggled and output in the opposite wave. This time, we will look at the clock source select bits. The clock source select bits are determined by 3 bits from 0 to 2 in TCCR0. These will be clock source 00, clock source 01, and clock source 02, respectively. So, This means clock source bits 0, 1, and 2 of timer counter 0. When all 3 bits are 0, no clock source occurs and no operation occurs. No action occurs. It doesn't work. Then, when it is 0, 0, 1, pre-scaling does not work and is immediately bypassed and the clock is transmitted to the timer. Dividing from 8 to 1024 is applied to the prescaler. So dividing is applied. As you can see here, starting from the timer counter 0, being stopped. 15.625 kHz corresponds to being divided with 1024. You can check out this interface in Code Wizard, AVR. So, please know that depending on the bit being divided, clock source 00, clock source 01, and clock source 02 become like this. This time, let's look at the prescaler diagram for timer counter 0. As you can see, when 16 MHz or 32.768 kHz comes in, non-free scaling, which is immediately bypassed, as you can see here, corresponds to division 1. It is set to stop when 0 is entered, and division can be applied starting from 8 up to 1024. ASSR selects 32.768 kHz by writing 1 to the AS0 bit. Please know that in order to change this division ratio, you must write 1 to the PSR0 bit, and then change the division ratio. We will take a closer look at the special function I/O registers. Now let's look at the second register, timer counter 0. The timer counter 0 register is used by timer counter 0. It is a register that allows immediate reading and writing access when operating as an upward or downward counter. If you change the TCNT0 value while the timer counter is running, in this case, you run the risk of missing OCR0. In the comparison match, the result in this case is called a glitch phenomenon. So you need to be careful and control this phenomenon. You need to be careful and control this phenomenon. You can check this in the C language code during your practice. OCR0 is used for compare match output register. OCR0 is output compare register 0. This is an 8-bit register that is managed continuously and continuously. You will manage it. How do you manage it? Comparison is made with TCNT0. They will be compared to C. If they match, the compare match output will be activated. Then, if the two registers match, the value set by the OC0 pin can be used as output by PWM or as an output comparison interrupt. So this can be used as a compare match when generating a PWM waveform as you see here. Or, it can be used to generate an OC0. Output, compare, interrupt. Then let us explain TCNT0 and OCR0. Using an analogy for easier understanding, TCNT0 will be the height we are currently climbing. So, in order to adjust the period, if we drive up to the parking lot, it will be excluded from the hiking time, so the period will become shorter. As the height of this parking lot increases, the period becomes shorter. Next, OCR0 is a rest area or shelter that may appear during the hiking. So, this rest area will play a role in generating a PWM waveform based on consistency with the TCNT0 value. So, it is a place to take a break. During the hiking, you can understand it this way. In the next video, you will have the opportunity to understand the meaning of TCNT and OCR values in more detail by actually calculating the period. Let's take a look at the asynchronous timer counter register. For this register, you only need to understand the AS0 bit correctly. This selects the clock source for timer counter 0. If you select 1, the clock input is selected. As the TOSC1 terminal in asynchronous mode. In this case, it operates in asynchronous mode. And, as you can see here, the kit's 32.768 kHz is selected as the clock of the timer counter 0. You can understand it in this sense. This clock is used to create 1 second. And now the 3 bits corresponding to 0, 1, and 2 all update the timer counter 0 and are busy checked to see if it is already in progress. Therefore, you can understand this as just a busy check bit. Bit 1 can be understood as the output compare. Register 0 update busy, a bit that checks whether the update is being executed. Timer counter control register 0 update bit corresponds to bit 0. These 3 bits are all part of checking whether an update is taking place. So even if you do not understand them precisely, there is no major problem in controlling the microprocessor. You have understood up to this point. Now, we need to consider a few things. If you perform a switching operation in timer counter 0 between synchronous mode and asynchronous mode, there is a possibility that an error may occur in timer counter 0, TCCR0, and OCR0. So we need to change the mode safely in the following order. Take a look at. As you can see here, the sequence continues sequentially from step 1 to step 6. You can take a look at this. The 5th register has arrived. This is a timer interrupt mask. You only need to understand the timer interrupt mask bits in register bits 0 and 1. First, the output compare match interrupt enable 0 is. As you can see here, this activates the comparison output and comparison match interrupt of timer counter 0. So, when OCIE 0 is defined as set, and the I bit, the 7th bit of the SREG status register, is set to 1, the output comparison interrupt is activated. This means that the output comparison interrupt of timer counter 0 is activated. If the timer counter 0 and OCR 0 are the values at which a match occurs, and which is the OCF 0 bit, is set to set in TIFR. The corresponding interrupt service routine is executed immediately. As you can see here, if you follow along like this, it compares with the timer counter 0. This interrupt service is activated. If bit 0 is recorded as 1, the overflow interrupt of timer counter 0 is used. So, in this case, when TOIE 0 is set, and the I bit, which is the 7th bit of the status register SREG, is set, the overflow interrupt is activated. When overflow from 0xFF to 0x00, an interrupt of timer counter 0 occurs, and the TOB 0 bit is set in the flag register TIFR. The corresponding interrupt service routine is executed. So, this TIFR is set, and the corresponding interrupt service routine is executed. If you look here, you can understand that the timer 0 overflow part is called directly. This time, we will look at TIFR. TIFR is truly a flag register. So, bit 0 of the timer counter interrupt flag register becomes 1 as the overflow flag bit of timer counter 0. When 1 is written, the overflow of timer counter 0 has been set. You can think of it that way. So, you just need to know that when an overflow occurs from 0xFF to 0x00, it becomes a set. It is automatically cleared when the interrupt handling routine is executed. Please understand that when the interrupt service routine is called, bit 0 of this timer interrupt flag register is automatically cleared to 0. Likewise, OCF 0 is also the output comparison flag bit. OCF 0 is set. When is it set? OCF 0 is set at the moment a match occurs between the timer counter register TCNT 0 and the output comparison match register OCR 0. This also has the characteristic of being automatically cleared after the interrupt handling routine is executed. So, when you actually control TIFR, You do not manipulate it. This time, we will finally look at the special function I/O register. For the special function I/O register, you only need to understand the TSM bit, bit 7, and the first bit, PSR 0 bit. Bit 7 is the keyword for timer counter synchronization mode. When you write 1 to the TSM bit, the timer counter is activated in synchronization mode. If you write 0 to the TSM bit, the PSR 0 and PSR 321 bits are cleared. In hardware, T-mid counter start simultaneously. Please understand that it is possible to perform actions that have those features to ensure synchronization. Bit 1, PSR 0, acts as a prescaler reset in timer counter 0. If 1 is written to the PSR 0 bit, the prescaler is reset. The prescaler of timer counter 0 is reset. What this means is that if you adjust the prescaler, write 1 to the TSM value and 1 to PSR 0, then adjust the corresponding prescaler. All you need to know is that if you write 0 to TSM again, all timers will be synchronized and run again. So, when you change the prescaler in the timer counter, you need to understand and operate the special function I/O register well. So far we have looked at timer counter register. Thank you.